This evening, we are going to embark upon a voyage that has the potential to fundamentally alter the way you perceive absolutely everything around you. We are going to investigate a subject that might appear simple on the surface, but in reality, it is completely mind-bending. We are going to uncover the actual scale of our home galaxy, the Milky Way, and determine where it truly resides within the grand cosmic order of existence. Because here is the thing that the vast majority of people fail to realize. The Milky Way is actually massive. It stands as one of the largest galaxies within the observable universe. However, at the very same time, when you pull back and zoom out far enough, it diminishes into almost nothingness. And believe me, by the conclusion of this exploration, you are going to feel a very distinct shift in how you view that band of luminescence you sometimes witness stretching across the dark night sky. Before we commence, if you find enjoyment in these types of deep explorations, a quick like or a subscribe would significantly assist in keeping this channel operational. It is a small gesture, but it means a great deal. Now, let us begin. Let us start with the facts that we are familiar with. You have likely heard people say that the Milky Way is big, and it certainly is big. In fact, it is more than just big. It is enormous. The Milky Way is one of the most colossal galaxies located in the entire observable universe. Now, I understand that this statement might sound surprising to you, particularly when you hear stories about the giant galaxies out there. But here is the truth that most individuals do not realize. The overwhelming majority of galaxies residing in the universe are actually tiny when compared to the Milky Way. Most galaxies are known as dwarf galaxies, which are merely small collections consisting of a few billion stars, or even fewer. The Milky Way, by comparison, is a true giant. The Milky Way stretches approximately 100,000 light-years from one side all the way to the other. That is a distance so enormous that light, which travels at a speed of roughly 186,000 miles per second, requires one full 100,000 years just to cross it. Think about that concept for a brief moment. The light originating from one edge of our galaxy will not reach the opposite edge for 100,000 years. Inside of this spiral structure, we possess somewhere between 100 billion and 400 billion stars. The exact number is difficult to pin down with precision because, well, attempting to count stars in a galaxy that you are currently residing inside of is comparable to trying to count all the trees in a vast forest while you are standing in the very middle of it. You are able to see some of them clearly, but the majority are hidden behind others, obscured by dust clouds and vast distances. Our Sun is merely one of these stars. It sits approximately 26,000 light-years away from the galactic center, tucked comfortably into a minor spiral arm known as the Orion Spur. We are not located at the center of anything particularly special. We are essentially in the suburbs of the galaxy, residing in a relatively quiet neighborhood where the stars are not packed together too densely and where supernova explosions occur rarely enough that life had a genuine chance to develop and survive. The Milky Way has served as our home for as long as human beings have existed. Every single star that you are able to see with your naked eye on a clear evening is a part of our galaxy. Every constellation, every shooting star, every planet visible in the heavens, all of it belongs to this singular structure. For the majority of human history, we did not even know that there was anything existing beyond it. But here is where matters become truly interesting. The Milky Way is genuinely large. In actual fact, approximately 95% of all the galaxies in the universe are smaller than the Milky Way. When astronomers survey galaxies across the cosmos, most of what they discover are small dwarf galaxies. The Milky Way is actually in the top 5% by size. That makes us exceptional, rather than merely average. Yet, despite being one of the largest galaxies around, when you begin zooming out, when you start looking at larger and larger structures, the Milky Way begins to shrink in its significance. Not in its actual size, but in its importance. It becomes merely one piece in structures so vast that they dwarf even a large galaxy such as ours. And that is the paradox that we are going to explore tonight. How the Milky Way can be both enormous and tiny at the exact same time, depending entirely on what scale you are viewing it from. But here is where things start to get fascinating. The Milky Way is not alone. It has neighbors, and lots of them. The closest large galaxy to us is Andromeda, which sits about 2.5 million light-years away. Now, Andromeda is actually bigger than the Milky Way. It contains around 1 trillion stars, which is more than twice the amount that we possess. It is also on a collision course with us. But do not worry, that event will not occur for another 4.5 billion years. And when it finally does happen, it will be more of a merger than a violent crash. The distances between stars are so vast that actual collisions between individual stars are incredibly unlikely. Then there are the Magellanic Clouds. These are 2 smaller galaxies that orbit the Milky Way. The Large Magellanic Cloud contains about 10 billion stars, and the Small Magellanic Cloud possesses a few billion stars. They are visible from the southern hemisphere as fuzzy patches in the night sky, and they have been known to humans for thousands of years. But people did not know they were separate galaxies until relatively recently. These galaxies, along with about 50 others, form what astronomers call the local group. It is basically our cosmic neighborhood. Most of the galaxies in the local group are small dwarf galaxies containing just a few billion stars or less. The Milky Way and Andromeda are the 2 dominant members. They are the big siblings in a family of smaller galaxies that orbit around them or float between them. The local group spans about 10 million light-years across. That sounds massive, and it certainly is. But here is the thing that starts to put our galaxy into perspective. The local group is just one tiny cluster in a much, much larger structure. The local group is part of something called the Virgo supercluster. Now, a supercluster is exactly what it sounds like. It is a cluster of galaxy clusters. Instead of individual galaxies, we are now talking about groups of galaxies, all gravitationally bound together in an enormous structure. The Virgo supercluster contains at least 100 galaxy clusters and groups. One of the largest is the Virgo cluster itself, which sits about 54 million light-years away from us and contains somewhere around 1,000 to 2,000 galaxies. Some of these galaxies are enormous, far bigger than the Milky Way. The Virgo supercluster as a whole contains about 100 trillion stars spread across about 110 million light-years. Let me put that into perspective for you. Remember how the Milky Way seemed big at 100,000 light-years across? The Virgo supercluster is 1,100 times wider. Our entire galaxy, with all of its hundreds of billions of stars, is just a tiny speck in this larger structure. If the Virgo supercluster were the size of a city, the Milky Way would be smaller than a single house in that city. Actually, it would be more like a single room in that house. But even this is not the full picture, because in the year 2014, astronomers discovered something even bigger. They found that the Virgo supercluster itself is just a small part of an even more massive structure called Lania Kea. The name comes from Hawaiian and means immeasurable heaven. which is fitting because Laniakea is almost incomprehensibly large. Laniakea is a supercluster of superclusters. It contains about 100,000 galaxies spread across 520 million light-years. All of these galaxies, including ours, are slowly moving towards the center of Laniakea, drawn by the combined gravity of all that mass. The Milky Way is not just sitting still in space. We are falling along with everything else in Laniakea toward a region called the Great Attractor. Now, here is where the scale really starts to mess with your head. If you shrunk Laniakea down so that the Milky Way was the size of a grain of sand, Laniakea itself would be about as big as a large room. We have gone from thinking our galaxy is everything to realizing it is less than a speck of dust in a structure so large it defies easy comprehension. But we are not done, not even close. Laniakea is huge, but it is still just one supercluster among many. When we zoom out even further, we see that the universe is filled with these structures, superclusters separated by vast voids, empty regions of space where very few galaxies exist. The universe at the largest scales looks like a cosmic web. Filaments of galaxies stretching across billions of light-years connected by threads and separated by enormous empty spaces. The observable universe, the part of the universe we can actually see, is about 93 billion light-years across. Why 93 billion and not smaller, given that the universe is only about 13.8 billion years old? It is because the universe has been expanding. Light from distant galaxies has been traveling toward us for billions of years. But during that time, the space itself has been stretching, carrying those galaxies even farther away. Within this observable universe, astronomers estimate there are about 2 trillion galaxies. Let that sink in for a moment. 2 trillion. And the Milky Way is just one of them. Not a special one. Not a particularly large one in this context. Just one among 2 trillion others. If we tried to represent this visually, if we made a scale model where every galaxy was represented by a single grain of sand, we would need enough sand to fill several Olympic-sized swimming pools. The Milky Way would be one grain in that vast collection, indistinguishable from all the others. Now, let us talk about the galaxies themselves in more detail, because understanding the full range of galaxy sizes is crucial to grasping where the Milky Way truly sits. And the key thing to remember is this. When most people hear about giant galaxies, they think those are the norm. They are not. Giant galaxies are the exception, not the rule. Let us start with IC 1101, one of the largest galaxies we have ever discovered. This galaxy is genuinely enormous. It is about 6 million light-years across. Remember, the Milky Way is 100,000 light-years across. IC 1101 is 60 times wider. If the Milky Way were a penny, IC 1101 would be a large pizza. IC 1101 contains about 100 trillion stars. That is roughly 250 times more stars than the Milky Way has. This single galaxy contains more stars than many entire galaxy clusters. It is so massive that if you replaced the Milky Way with IC 1101, it would stretch far beyond our nearest neighboring galaxies. Andromeda, which sits 2.5 million light-years away, would actually be inside IC 1101's boundaries. But here is what you need to understand. IC 1101 is not normal. It is exceptional. It is one of the largest galaxies we have ever found. Galaxies like IC 1101 are incredibly rare. Out of the trillions of galaxies in the observable universe, only a tiny fraction are this large. Then there is NGC 6166, also known as the Medusa merger. This galaxy is the result of two large spiral galaxies that collided billions of years ago. It is extremely elongated, stretching about 700,000 light-years from end to end. That is 7 times the width of the Milky Way. The collision that created it triggered massive bursts of star formation, and even now, billions of years later, the galaxy is still forming new stars at a rate far higher than the Milky Way. Again, impressive, but also rare. Most galaxies never undergo such dramatic mergers that create these elongated structures. The giant ellipticals are perhaps the most striking examples. A galaxy called A2261 BCG, which sits at the center of a galaxy cluster about 3 billion light-years away, is roughly 2 million light-years across. That is 20 times the width of the Milky Way. It contains about 10 trillion stars, all packed into a roughly spherical shape. This galaxy formed by cannibalizing other galaxies, consuming them over billions of years, and growing larger and larger. These giant ellipticals are typically found at the centers of galaxy clusters, where their gravity has allowed them to consume many smaller galaxies over time. They are the kings of their neighborhoods, having grown fat by eating their neighbors. So yes, compared to these absolute monsters, the Milky Way is smaller. But let us put this in perspective. For every IC1101 or A2261 BCG, there are thousands upon thousands of galaxies smaller than the Milky Way. The most common galaxies in the universe are dwarf galaxies. These contain anywhere from a few million to a few billion stars. They are typically just a few thousand light-years across, and they are everywhere, absolutely everywhere. The local group, our cosmic neighborhood, contains about 50 known galaxies. The Milky Way and Andromeda are the two giants. Then there is Triangulum, a smaller spiral, and then there are dozens of dwarf galaxies, the Large Magellanic Cloud, the Small Magellanic Cloud, and dozens of tiny dwarf spheroidal galaxies that most people have never heard of. This pattern repeats across the universe. Every large galaxy is surrounded by dozens or hundreds of smaller satellite galaxies. The Andromeda Galaxy has its own collection of dwarf satellites. M87 has dozens of dwarf galaxies orbiting it. Wherever you find a large galaxy, you find many small ones. So when we talk about galaxy sizes, we have to be clear about what we are comparing. If we are comparing the Milky Way to the largest galaxies in the universe, then yes, it is smaller. But those largest galaxies are rare. They are the outliers. They are the exceptions. If we are comparing the Milky Way to the average galaxy, to the typical galaxy you would encounter if you randomly selected one from the universe, then the Milky Way is huge, vastly larger, incomparably larger in many cases. The typical galaxy in the universe is a dwarf. It contains maybe a billion stars, maybe less. It is a few thousand light-years across. It is faint, hard to see, and unremarkable. The Milky Way, with its hundreds of billions of stars and 100,000 light-year span, is exceptional by comparison. Think of it this way. If you gathered 1,000 random galaxies from across the universe, probably 950 of them would be smaller than the Milky Way. Maybe 40 would be roughly similar in size, and maybe 10 would be larger, with only 1 or 2 being dramatically larger, like IC1101. The Milky Way is not in the top 1%, but it is comfortably in the top 5%. And that makes it large, genuinely large by cosmic standards. It is worth taking a moment to talk about the different types of galaxies and where the Milky Way fits in this cosmic zoo. Astronomers classify galaxies into several main types: spirals, ellipticals, and irregulars. But within these categories, there is enormous variety. and understanding this variety helps us see just how the Milky Way truly measures up. Spiral galaxies like the Milky Way have flat disks with spiral arms extending from a central bulge. They are usually blue and full of young, hot stars, especially in their spiral arms. Spiral galaxies are still actively forming stars. They have plenty of gas and dust that can collapse to create new stars. The Milky Way forms about 1 or 2 new stars every year, which might not sound like much, but it adds up over millions of years. But not all spiral galaxies are the same size. Some spiral galaxies are much larger than the Milky Way. NGC 6309, for instance, is a spiral galaxy about 400,000 light-years across. That is 4 times the diameter of the Milky Way. It is sometimes called the box galaxy because from certain angles it looks rectangular rather than spiral. This galaxy sits about 52 million light-years away in the constellation Draco. Then there is Malin 1, discovered in the year 1986 by astronomer David Malin. This is what is called a giant low-surface brightness spiral galaxy. It is about 650,000 light-years across, making it more than 6 times wider than the Milky Way. The interesting thing about Malin 1 is that it is very faint. Even though it is huge and contains a lot of stars, those stars are spread out over such a large area that the galaxy is hard to see. It took until the mid-1980s to discover it. Despite it being relatively nearby in cosmic terms, these giant spirals show us that while the Milky Way is large, there are still bigger spirals out there. But here is what is crucial to understand. These giant spirals are rare. Very rare. For every galaxy like NGC 6309 or Malin 1, there are thousands of galaxies smaller than the Milky Way. Elliptical galaxies, on the other hand, are mostly red and orange. They contain old stars and very little gas or dust. Star formation in ellipticals has mostly stopped. They are considered retired galaxies that have already lived through their most active phase. Many ellipticals formed through galaxy mergers. When 2 spiral galaxies collide, their beautiful spiral structures get disrupted, and the end result is often an elliptical galaxy. But elliptical galaxies vary enormously in size. The smallest ellipticals, called dwarf ellipticals, might contain only a few million stars. They are tiny, often just a few thousand light-years across. M32, a dwarf elliptical galaxy that orbits Andromeda, is only about 6,500 light-years across. That is 15 times smaller than the Milky Way. And galaxies like M32 are incredibly common. They are everywhere. On the other extreme are the giant and supergiant ellipticals. These monsters can contain trillions of stars and stretch for millions of light-years. They are typically found at the centers of galaxy clusters, where they have had billions of years to consume smaller galaxies that wandered too close. M87, which I mentioned earlier, is a supergiant elliptical galaxy in the Virgo cluster. It is about 120,000 light-years across, slightly larger than the Milky Way in diameter, but it contains far more stars, around 1 trillion compared to our few hundred billion. More importantly, M87's mass is much greater when you include its dark matter halo. M87 is several times more massive than the Milky Way. M87 is also famous for being the first galaxy where we directly imaged a black hole. In 2019, the Event Horizon Telescope collaboration released an image showing the shadow of M87's central supermassive black hole. This black hole has a mass of about 6.5 billion times the mass of our Sun. To put that in perspective, the black hole at the center of the Milky Way, Sagittarius A star, is only about 4 million solar masses. M87's black hole is more than 1,600 times more massive. These giant ellipticals are impressive, no doubt. But here is the key point. They are extremely rare. Most galaxies in the universe are not giants like M87. Most galaxies are dwarfs. Irregular galaxies do not fit into either category. They have no clear shape, often because they have been disrupted by gravitational interactions with other galaxies. The Large and Small Magellanic Clouds are examples of irregular galaxies. They are small and chaotic, lacking the organized structure of spirals or the smooth shape of ellipticals. The Large Magellanic Cloud is about 14,000 light-years across and contains maybe 10 billion stars. The Small Magellanic Cloud is even smaller, about 7,000 light-years across, with a few billion stars. These are tiny compared to the Milky Way, but they are not the smallest galaxies out there. Ultra-faint dwarf galaxies discovered in large numbers over the past couple of decades are the smallest galaxies we know of. Some contain only a few thousand stars and are just a few hundred light-years across. Segway 1, for example, discovered in the year 2006, contains only about 1,000 stars. It is so small and faint that it is barely a galaxy at all. It is more like a large star cluster that happens to be bound by its own gravity. These tiny galaxies are interesting because they are thought to be similar to the building blocks that merged to form larger galaxies like the Milky Way. In the early universe, the first galaxies were probably all small dwarf-sized objects. Over billions of years, they merged together, forming progressively larger galaxies. Now, here is the crucial fact. When astronomers survey the universe, these dwarf galaxies are what they find most often. The universe is absolutely packed with dwarf galaxies. For every large galaxy, like the Milky Way, there are probably hundreds or even thousands of dwarf galaxies. The Milky Way itself has about 50 known satellite dwarf galaxies orbiting it. So when we say the Milky Way is one of the largest galaxies in the universe, that is absolutely true. About 95% of all galaxies are smaller than the Milky Way. If you lined up all the galaxies in the universe by mass, the Milky Way would be in the top 5%. That is genuinely impressive. The Milky Way is not an average galaxy. It is a large, massive spiral that contains hundreds of billions of stars. Most galaxies will never have that many stars. Most galaxies are small, faint dwarfs that contain just a fraction of the Milky Way's stellar population. But, and this is a big but, when you compare the Milky Way to the very largest galaxies, to the giant and supergiant ellipticals like M87 or IC 1101, then yes, the Milky Way is smaller. And when you start looking at larger structures, superclusters, and cosmic filaments, the Milky Way becomes just one piece in something much vaster. That is the paradox we are exploring. The Milky Way is simultaneously one of the largest galaxies and also tiny compared to the largest structures. Both things are true. Beyond just size, there are galaxies out there that are extreme in other ways. Let me tell you about some of the most unusual galaxies astronomers have discovered, because these comparisons also help put the Milky Way in perspective. There is NGC 4889, sometimes called the Coma B galaxy. It is an elliptical galaxy about 300,000 light-years across, 3 times the width of the Milky Way. But what makes it unusual is its extremely bright and active nucleus. The center of this galaxy is forming stars at a rate of about 150 stars per year. That is roughly 100 times faster than the Milky Way. This burst of star formation was probably triggered by a collision with a smaller galaxy millions of years ago. Then there is the Sombrero Galaxy, M104. This is a spiral galaxy seen almost edge-on, and it has an unusually large central bulge. The bulge is so prominent that the galaxy looks more like an elliptical with a thin disk around it than a typical spiral. The Sombrero Galaxy is about 50,000 light-years across, about half the size of the Milky Way. But its central black hole is enormous, about 1 billion solar masses. That is 250 times more massive than the black hole at the center of the Milky Way. Despite the galaxy being smaller, the Tadpole Galaxy, UGC 10214, is a disrupted spiral galaxy with an enormous tail of stars stretching out behind it. The tail is about 280,000 light-years long. What happened was another galaxy passed close by, and the gravitational interaction pulled stars and gas out of the Tadpole Galaxy, creating this long stream. The galaxy itself is about 180,000 light-years across, nearly twice the width of the Milky Way, and the whole structure, including the tail, spans about 400,000 light-years. Hoag's object is one of the strangest galaxies ever discovered. It is a ring galaxy where a perfect ring of young blue stars surrounds an older yellow core with almost nothing in between. The ring is about 100,000 light-years across, similar to the Milky Way's diameter, but the structure is completely different. No one is entirely sure how ring galaxies form. The leading theory is that they result from a collision where a smaller galaxy passed directly through the center of a larger disk galaxy, creating a ripple that became a ring. But Hoag's object is so perfect and symmetrical that this explanation seems almost too simple. Centaurus A is a peculiar galaxy that is a hybrid of an elliptical and spiral. It is an elliptical galaxy with a prominent dust lane cutting across its middle. And this dust lane is actually a smaller spiral galaxy that Centaurus A is in the process of consuming. The galaxy is about 60,000 light-years across, smaller than the Milky Way, but it is extremely active. Its central black hole is feeding on the infalling material, producing enormous jets of matter and energy that extend for millions of light-years into space. These jets are among the largest structures produced by any galaxy, far exceeding anything the Milky Way has ever produced. The antennae galaxies, NGC 4038 and NGC 4039, are two spiral galaxies in the process of colliding. They are named for their long tidal tails that extend outward like insect antennae. Each galaxy was probably similar in size to the Milky Way before the collision, but now the whole structure spans about 500,000 light-years. The collision has triggered massive star formation. Thousands of new star clusters are forming in the regions where the two galaxies overlap. This is a preview of what might happen when the Milky Way and Andromeda collide billions of years from now. These extreme galaxies show us the incredible variety in the universe. The Milky Way, by comparison, is pretty normal. It is not undergoing any major collisions. It is not forming stars at an extreme rate. It does not have unusual structures like rings or jets. It is just a regular spiral galaxy going about its business of slowly rotating and forming a few new stars every year. And that normality is actually a good thing. Extreme galaxies, while fascinating, are often chaotic places. The bursts of star formation that accompany galaxy collisions also produce lots of supernovae, which release deadly radiation. The active galactic nuclei powered by feeding black holes can sterilize large regions of their host galaxies with intense radiation. The Milky Way's quiet, steady existence has allowed planetary systems like ours to form and remain stable for billions of years. If we lived in one of those extreme galaxies, Earth might have been sterilized by radiation long ago. Our normality, our averageness, might be exactly what life needs. Let me come back to IC 1101 for a moment, because this galaxy really deserves more attention. It was discovered in the year 1790 by a British astronomer named William Herschel. Though at the time no one realized how massive it was not until more recent observations, particularly from the Hubble Space Telescope, that astronomers figured out its true size. IC 1101 is what is called a supergiant elliptical galaxy. It sits at the center of the Abell 2029 galaxy cluster, about 1.07 billion light-years from Earth. Its mass is estimated at around 100 trillion times the mass of our Sun. The Milky Way, by comparison, has a mass of about 1.5 trillion solar masses, including all its dark matter. IC 1101 is roughly 60 to 70 times more massive. What makes IC 1101 so large? It grew by consuming other galaxies. Galaxy clusters are violent places. Galaxies regularly pass close to each other, and when they do, the larger galaxy's gravity can rip stars away from the smaller one. Over billions of years, a galaxy at the center of a cluster can consume dozens or even hundreds of smaller galaxies, growing larger and larger. If you lived on a planet in IC 1101, your night sky would be absolutely packed with stars. The density of stars near the galaxy's center is thousands of times higher than in the Milky Way. You would see stars in every direction, close enough that some would shine as bright as Venus or Jupiter appear in our sky. Constellations would be meaningless because the stars would form a nearly continuous glow. But here is something that really puts the Milky Way in perspective. IC 1101 is not unique. There are thousands of giant elliptical galaxies scattered throughout the universe. A 2261 BCG, the galaxy I mentioned earlier, is even larger. And there are others. M87 in the Virgo cluster contains about 1 trillion stars and has a supermassive black hole at its center that is 6.5 billion times the mass of the Sun. For comparison, the black hole at the center of the Milky Way is only about 4 million solar masses. These galaxies are the true giants of the universe. Next to them, the Milky Way is small. Not tiny, not insignificant, but definitely small. Earlier, I mentioned that our galaxy is moving towards something called the Great Attractor. This deserves a deeper explanation because it is one of the most fascinating discoveries in modern astronomy. Astronomers in the 1970s noticed something strange. When they measured the motion of our galaxy and nearby galaxies, they found that we are all moving in a particular direction at about 600 kilometers per second. That is over 1 million miles per hour. This motion is separate from the universe's expansion. Something is pulling us. The problem was when astronomers looked in that direction, they could not see anything obvious that would cause such a strong gravitational pull. The region lies behind the plane of the Milky Way, where dust and gas block our view. It took decades of observations using different types of light, X-rays, infrared, radio waves, to piece together what was there. What they found was a massive concentration of galaxies called the Norma cluster. This cluster and the surrounding regions contain an enormous amount of mass, enough to pull thousands of galaxies toward it. But even the Norma cluster was not enough to explain all the motion. There had to be something even larger pulling us. That something turned out to be the Shapley supercluster, an enormous collection of galaxies about 650 million light-years away. It is one of the largest structures in the nearby universe, containing thousands of galaxies with a total mass of about 10,000 trillion times the mass of the Sun. The combined gravity of all these galaxies is what is pulling the Milky Way and everything else in our region of space. But here is where it gets even more interesting. Recent observations have shown that even the Shapley supercluster is moving. There might be something even larger and more distant pulling it. The universe at the largest scales is a complex web of motion with structures pulling on other structures in ways we are still trying to understand. The point is this: the Milky Way is not a fixed point in space. We are falling along with thousands of other galaxies toward concentrations of mass that are so large they dwarf our entire local group. Our galaxy is just a tiny piece of cosmic driftwood caught in currents we can barely measure. Now let us talk about what is between these superclusters, because the voids are just as important for understanding scale as the clusters themselves. When you map out the distribution of galaxies in the universe, you find that they are not evenly spread. Instead, they cluster along filaments forming a cosmic web. Between these filaments are vast empty regions called voids. The largest known void is the KBC void, named after astronomers Ryan Keenan, Amy Barger, and Lennox Cowie, who studied it extensively. This void is roughly 2 billion light-years across. Inside it, there are very few galaxies. It is not completely empty, but the density of galaxies is much lower than in surrounding regions. Think about that scale for a moment. A void 2 billion light-years across. If you were somehow transported to the center of this void and looked out in any direction, the nearest significant galaxy clusters would be about 1 billion light-years away. At that distance, even a giant galaxy would appear as just a faint smudge, barely visible, even with powerful telescopes. Our Milky Way could fit across the width of the KBC void 20,000 times. The entire local group would be a barely visible speck. Even Laniakea, that immense supercluster containing 100,000 galaxies, would fit across the KBC void less than 4 times. These voids make up about 80% of the universe's volume. Most of space is empty. The galaxies, superclusters, and filaments occupy only a small fraction of the total volume. It is like the universe is a vast ocean with islands of matter scattered throughout. And the Milky Way is a single grain of sand on one of those islands. Before we get to the Hercules Corona Borealis Great Wall, let us talk about some other massive structures that make the Milky Way look tiny. The universe is not just filled with individual galaxies, it is filled with structures made of galaxies, and these structures are absolutely enormous. The Sloan Great Wall was discovered in the year 2003 by astronomers analyzing data from the Sloan Digital Sky Survey. This is a wall of galaxies that stretches about 1.37 billion light-years across. It is located about 1 billion light-years from Earth, and it contains tens of thousands of galaxies. To put that in perspective, if the Milky Way were the size of a grain of rice, the Sloan Great Wall would be about the length of a football field. Actually, that is understating it. If the Milky Way were a grain of rice, the Sloan Great Wall would be longer than 10 football fields placed end to end. This structure was discovered by mapping the 3-dimensional positions of galaxies. When you plot where galaxies are in space, not just where they appear on the sky, but how far away they are, patterns emerge. Galaxies are not randomly distributed. They cluster along filaments and walls surrounding vast empty voids. The Sloan Great Wall is one of these walls. It is a sheet of galaxies, relatively thin, but extremely long and wide. Think of it like a cosmic membrane stretching across more than 1 billion light-years of space. The galaxies within it are gravitationally connected, though loosely. They are all part of the same large-scale structure. What is remarkable about the Sloan Great Wall is that it was completely unknown until recently. It is not that we could not see the galaxies that make it up. Many of those galaxies had been observed decades earlier, but we did not know they formed a coherent structure until we had good distance measurements for enough galaxies to map out their three-dimensional positions. This discovery showed that the universe has structure on scales much larger than anyone had previously realized. Superclusters like Laniakea are huge, spanning hundreds of millions of light-years. But walls like the Sloan Great Wall are even larger, spanning more than 1 billion light-years. Then there is the CFA2 Great Wall, discovered even earlier in 1989. This is another filament of galaxies about 500 million light-years long, 200 million light-years wide, and 15 million light-years thick. It is smaller than the Sloan Great Wall, but still enormous. It contains tens of thousands of galaxies, including some very large ones. The CFA2 Great Wall is closer to us than the Sloan Great Wall, about 200 million light-years away. The Virgo supercluster, which contains the Milky Way, is actually part of this structure. So in a sense, we live on one of these cosmic walls. But the Milky Way is just one tiny galaxy among tens of thousands that make up the wall. These discoveries changed how astronomers think about the universe's structure. In the early 20th century, galaxies were thought to be more or less randomly distributed in space. Sure, there were clusters, groups of galaxies bound together by gravity, but those clusters were thought to be isolated islands in an otherwise empty void. By the late 20th century, it became clear that this was not true. Galaxies are not randomly distributed. They form a cosmic web with filaments and walls surrounding voids. The voids are enormous regions, sometimes hundreds of millions of light-years across, where very few galaxies exist. Between the voids, galaxies cluster along filaments and walls. This cosmic web structure is thought to be a result of how the universe evolved. In the very early universe, tiny density fluctuations existed in the distribution of matter. Some regions were slightly denser than average, others slightly less dense. Over billions of years, gravity amplified these fluctuations. Denser regions attracted more matter, becoming even denser. Less dense regions lost matter to their surroundings, becoming voids. The result is the cosmic web we see today. Filaments of galaxies stretching across hundreds of millions or billions of light-years, surrounding voids that are nearly empty. And the Milky Way, it is just one galaxy in this vast web sitting on a filament, part of a structure that is far, far larger than itself. Computer simulations of the universe's evolution running on some of the most powerful supercomputers in the world reproduce this cosmic web structure by starting with the conditions that existed shortly after the Big Bang and letting gravity do its work. These simulations show the formation of filaments and voids that look remarkably similar to what we observe in the real universe. These simulations also show that the cosmic web is not just made of visible matter, stars, and gas. It is primarily made of dark matter. The dark matter forms the scaffolding, the underlying structure. Visible matter falls into this scaffolding, collecting in the densest regions where it can form galaxies and stars. So when we talk about structures like the Sloan Great Wall, we are really talking about a concentration of dark matter that happens to contain tens of thousands of galaxies. The galaxies are just the visible parts, like lights on a Christmas tree. The tree itself, the structure that holds everything together, is made of dark matter. The Milky Way sits in this cosmic web held by dark matter connected to other galaxies through filaments of dark matter. We are part of something much larger than ourselves, and that something is incomprehensibly vast. If voids show us how empty the universe can be, then the largest structures show us how much matter can cluster together. The Hercules Corona Borealis Great Wall is the largest known structure in the universe. It is a galactic filament, basically a long string of galaxy clusters that stretches across about 10 billion light-years. To put that in perspective, the Milky Way is 100,000 light-years across. The Hercules Corona Borealis Great Wall is 100,000 times larger. If you traveled at the speed of light, it would take you 100,000 years to cross the Milky Way. It would take you 10 billion years to cross this structure. That is more than 70% of the age of the universe itself. This structure contains billions of galaxies. The total mass is almost impossible to comprehend. And yet, even this enormous structure is just one part of the universe's cosmic web. There are other giant walls and filaments, slightly smaller, but still staggeringly large. The existence of structures this large actually created a problem for cosmologists. According to our understanding of how the universe evolved, there should not be enough time for structures this large to form. The universe is only 13.8 billion years old. Gravity works slowly. It takes time for matter to clump together into galaxies, and even more time for those galaxies to cluster into groups and superclusters. Computer simulations of the universe's evolution predicted that the largest structures should be no more than 1.2 billion light-years across. The Hercules Corona Borealis Great Wall is roughly 10 times larger than that. Its existence suggests that either our models are wrong or incomplete, or that the universe is stranger than we thought. Either way, the takeaway is clear. The Milky Way, sitting in its little corner of the Virgo supercluster, is utterly insignificant compared to structures like this. Our entire galaxy could be copied 10 billion times and strung end to end, and it would just barely match the length of one cosmic filament. To really understand how small the Milky Way is, it helps to understand how galaxies form in the first place. Because the story of galaxy formation is really a story about scale, about how small things combine to make bigger things, and how even the biggest things are small compared to the universe as a whole. In the beginning, just after the Big Bang, the universe was almost perfectly uniform. Matter was spread evenly throughout space, with only tiny variations in density. These variations, called quantum fluctuations, were incredibly small. We are talking about density differences of maybe 1 part in 100,000. But those tiny differences were enough in regions that were slightly denser than average. Gravity pulled in more matter. As more matter accumulated, the gravitational pull became stronger, attracting even more matter. This is what astronomers call gravitational collapse. It is a runaway process where dense regions get denser and denser. The first structures to form were small. In the first few 100 million years after the Big Bang, the universe was forming what we now call mini halos. These were clumps of dark matter, each containing maybe 1,000,000 times the mass of the Sun. Visible matter, hydrogen and helium gas, fell into these dark matter halos and began to form the first stars. These first stars were different from stars today. They were made of pure hydrogen and helium, with no heavy elements. They were also enormous, often 100 or more times the mass of the Sun. These massive stars lived fast and died young, exploding as supernovae after just a few million years. But their deaths enriched the surrounding gas with heavy elements. The next generation of stars could form from gas that contained carbon, oxygen, iron, and other elements. This allowed for more complex chemistry, and eventually for rocky planets to form. As time went on, these mini halos merged. 2 mini halos would fall together, their dark matter combining, their stars mixing. The result was a slightly larger halo with more stars. This process repeated over and over. small structures merged to form larger structures. By about 1 billion years after the Big Bang, the first true galaxies had formed. These early galaxies were small by today's standards, maybe a few billion stars, much smaller than the Milky Way. But they were growing, consuming gas from their surroundings and merging with other small galaxies. The Milky Way formed through this process. It was not created all at once. It grew gradually over billions of years through mergers and accretion. The oldest stars in the Milky Way found in the halo and globular clusters formed more than 13 billion years ago in some of those early small galaxies. As those small galaxies merged, their stars became part of the Milky Way. Studies of the chemical composition of stars in the Milky Way have revealed this history. Different stars have different ratios of elements reflecting the conditions in the gas clouds from which they formed. By analyzing these chemical signatures, astronomers can identify groups of stars that formed together in the same ancient galaxy before it merged with the Milky Way. This field, called galactic archaeology, is revealing the Milky Way's family tree. We can now identify several ancient dwarf galaxies that merged with the Milky Way billions of years ago. Each one contributed its stars to our galaxy. In a sense, the Milky Way is not a single entity, but a composite, a collection of many smaller galaxies that merged over time. And this process continues today. The Sagittarius dwarf elliptical galaxy is currently merging with the Milky Way. Over the next few billion years, it will be completely absorbed, its stars becoming part of the Milky Way's halo. The large and small Magellanic Clouds will eventually meet the same fate. This process of growth through mergers is common to all large galaxies. The giant ellipticals at the centers of galaxy clusters grew by consuming dozens or even hundreds of smaller galaxies. They are like cosmic snowballs rolling through space and gathering mass. But there is a limit to this growth. Galaxy mergers are most common when galaxies are close together, which was more common in the early universe when everything was more tightly packed. As the universe expands, galaxies spread out. The distances between them grow. Mergers become less common. Today, major mergers between large galaxies are relatively rare. When they do happen, they are spectacular events that trigger bursts of star formation and can completely transform both galaxies. But most galaxies now grow slowly, accreting gas from their surroundings and occasionally consuming small dwarf galaxies. The Milky Way's merger with Andromeda in about 4.5 billion years will be one of these rare major mergers. The result will be a large elliptical galaxy containing about 1.5 trillion stars. It will be one of the larger galaxies in the local group, but still nothing special on cosmic scales. There are many elliptical galaxies in the universe that are just as large or larger. Understanding galaxy formation also helps us understand why galaxies have the sizes they do. Galaxy size is determined by the mass of the dark matter halo. A larger halo can hold more visible matter, allowing for a larger galaxy. The Milky Way's dark matter halo contains about 1 trillion times the mass of the Sun. Galaxies with more massive halos, like IC 1101 with its 60 to 100 trillion solar mass halo, are correspondingly larger. But dark matter halos do not grow indefinitely. In the early universe, when matter was more densely packed, halos could grow quickly by merging with nearby halos. As the universe expanded and matter spread out, halo growth slowed. Today, most dark matter halos are growing very slowly, if at all. This means that the Milky Way is probably close to its maximum size, at least until it merges with Andromeda. It might consume a few more dwarf galaxies over the next few billion years, but these will add relatively little mass. The Milky Way today is not that different in size from the Milky Way a few billion years ago, and it will not be that different a few billion years from now, at least until the Andromeda merger. In the grand scheme of galaxy evolution, the Milky Way is a middle-aged galaxy that has largely stopped growing. It has reached a stable size and will remain roughly this size until its merger with Andromeda changes everything. Let us zoom back out and think about our cosmic neighborhood in more detail, because the local group itself tells us something important about the Milky Way's size and significance. The local group, as I mentioned, contains about 50 galaxies, but most of these are dwarf galaxies, small and faint. Only 3 galaxies in the local group are large spirals: the Milky Way, Andromeda, and Triangulum. Andromeda, also called M31, is the largest member of the local group. It contains about 1 trillion stars, more than twice what the Milky Way has. It is about 220,000 light-years across, more than twice the Milky Way's diameter. And it is more massive overall, with a dark matter halo that contains more mass than the Milky Way's halo. In our little cosmic neighborhood, the Milky Way is the second biggest galaxy. That might sound impressive until you remember there are only about 50 galaxies in the local group, and most of them are tiny. Being second in a group of 50, where most of the others are much smaller, is not that special. The Triangulum galaxy M33 is the 3rd largest spiral in the local group. It contains about 40 billion stars and is about 60,000 light-years across. It is less than half the size of the Milky Way, and it might actually be a satellite of Andromeda orbiting it, rather than being an independent member of the local group. The rest of the local group's galaxies are dwarfs. The Large Magellanic Cloud has about 10 billion stars. The Small Magellanic Cloud has a few billion. Most of the dwarf galaxies have fewer than 1 billion stars, and some have only a few million. So yes, the Milky Way is one of the largest galaxies in the local group, but the local group itself is not particularly impressive on cosmic scales. It is a small collection of galaxies in a relatively quiet corner of the Virgo supercluster. Compare our local group to the Virgo cluster, the large galaxy cluster at the heart of the Virgo supercluster. The Virgo cluster contains about 1,000 to 2,000 galaxies. Many of these are much larger than anything in the local group. M87, which I have mentioned several times, dominates the Virgo cluster. It is the largest galaxy in the cluster, and it is much larger than either the Milky Way or Andromeda. Its gravitational influence extends across the entire cluster. There are other giant ellipticals in the Virgo cluster like M84 and M86. These are also larger than the Milky Way, and there are numerous large spiral galaxies comparable in size to the Milky Way or larger. If the Milky Way were in the Virgo cluster instead of the local group, it would be just another medium-sized spiral. Nothing special, probably not even in the top 50% by size. But we are not in the Virgo cluster. We are in the local group in a quieter region of the supercluster, and that is probably a good thing for life. Galaxy clusters are violent places. Galaxies pass close to each other regularly. Gravitational interactions strip gas and stars from galaxies. The space between galaxies is filled with hot X-ray emitting gas. In a cluster like Virgo, the Milky Way might have lost much of its gas to these interactions. Without gas, we could not form new stars. Our galaxy would be aging, running out of fuel, slowly dying. Being in a small group like the local group means we are more isolated. We have avoided many of the violent interactions that cluster galaxies experience. We have been able to retain our gas and continue forming stars. This stability might have been crucial for life on Earth. So, while the local group is small, and the Milky Way is just the second largest galaxy in it, this modest position might be exactly what we need. Sometimes being small and out of the way is better than being large and in the thick of things. Let us shift gears for a moment and talk about what all this means for the question of life in the universe. With 2 trillion galaxies in the observable universe, and each galaxy containing anywhere from millions to trillions of stars, the total number of stars is absolutely staggering. Astronomers estimate there are about 200 billion trillion stars in the observable universe. That is a 2 followed by 23 zeros. Many of these stars have planets. The Kepler Space Telescope showed us that planets are common, not rare. Most stars have at least one planet, and many have several. If even a tiny fraction of these planets are capable of supporting life, the numbers become enormous. If just 1 in every million planets can support life, that is still 200 trillion potential homes for life. And if intelligent life arises on just 1 in every million of those life-bearing planets, that is still 200 billion civilizations in the observable universe. Yet, we have never detected a signal from any of them. The galaxy seems silent. This is the Fermi paradox, and it is one of the deepest mysteries in science. Where is everybody? Maybe life is rarer than we think. Maybe the jump from simple life to complex life is incredibly difficult. Maybe intelligent civilizations destroy themselves before they can spread. Maybe they are out there but staying quiet. Maybe they are communicating in ways we cannot detect yet. Or maybe, and this is the humbling possibility, space is just too big. The distances between stars are so vast that even if civilizations are common, they might never encounter each other. The Milky Way is 100,000 light-years across. A radio signal from the other side of the galaxy would take 100,000 years to reach us. By the time it arrived, the civilization that sent it might be long gone. And if civilizations are spread across all 2 trillion galaxies, the nearest galaxy, Andromeda, is 2.5 million light-years away. A signal from there would take 2.5 million years to reach us. Most galaxies are billions of light-years away. The universe is so large that civilizations could exist in enormous numbers and still never make contact with each other. The scale of the universe is not just humbling, it is isolating. Even if we are not alone, we might effectively be alone because the distances are simply too great to bridge. Now, let us talk about the observable universe and what lies beyond it. When we say the observable universe is 93 billion light-years across, what we mean is that is the limit of what we can possibly see. Light from anything farther away has not had time to reach us yet. The universe is 13.8 billion years old. You might think that means we can see 13.8 billion light-years in every direction, making the observable universe about 27.6 billion light-years across. But the universe has been expanding the whole time. The space itself has been stretching. So, a galaxy that emitted light 13 billion years ago has moved much farther away during the time its light has been traveling toward us. By the time that light reaches us, the galaxy might now be 46 billion light-years away. That is why the observable universe is about 93 billion light-years across. It is the maximum distance from which light has had time to reach us, accounting for the expansion of space. But here is the thing. The observable universe is just what we can see. The actual universe is almost certainly much larger. It might even be infinite. We have no way of knowing because we cannot see beyond the observable limit. Think about what that means. The Milky Way, sitting in its little corner of space, is part of an observable universe that contains 2 trillion galaxies. But that observable universe might be just a tiny fraction of the total universe. If the universe is infinite, then the observable universe, vast as it is basically nothing. 0% of infinity is still 0. And our galaxy in an infinite universe, the Milky Way, is not just small. It is infinitesimally small. It is less than a grain of sand on a beach. It is less than an atom in the Earth. It is so small that there are not really adequate comparisons. Some theories in physics go even further. They suggest that our universe might be just one of many in a multiverse. These theories arise from attempts to understand quantum mechanics and cosmic inflation, the rapid expansion that occurred in the first fraction of a second after the Big Bang. According to eternal inflation theory, the Big Bang was not a single event. It is happening constantly, creating bubble universes that spawn more bubble universes. Our universe would be just one bubble in an infinite foam of universes, each with potentially different laws of physics. In some versions of quantum mechanics, every time a quantum event has multiple possible outcomes, the universe splits and all outcomes occur in different branches. This would create an infinite number of parallel universes, one for every possible outcome of every quantum event. Now, these ideas are speculative. We have no way to observe other universes. So these theories are hard to test. But they are taken seriously by many physicists because they arise naturally from well-established theories. If the multiverse exists, then our universe, already unimaginably large, is just one of many, and the Milky Way, it becomes even more insignificant. Not just small compared to our universe, but small compared to an infinite collection of universes. Even if you do not believe in the multiverse, even if you think our universe is all there is, the scale is still overwhelming. The Milky Way is one galaxy among 2 trillion in the observable universe, which itself might be just a tiny visible fraction of a much larger or infinite total universe. Let us take a step back and think about what all this means. We started by talking about the Milky Way, our home galaxy, a spiral containing hundreds of billions of stars. It seemed big, and it is big by human standards. But then we compared it to the local group, to the Virgo supercluster, to Laniakea, to the cosmic web of filaments and voids. We compared it to giant galaxies like IC 1101 that are 60 times larger. We compared it to structures like the Hercules Corona Borealis Great Wall that are 100,000 times larger. We compared it to the observable universe that contains 2 trillion galaxies, and possibly to a total universe that might be infinite. At every step, the Milky Way got smaller. Not physically smaller, obviously. It is still 100,000 light-years across, but smaller in significance, less special, more ordinary. This is a humbling realization, but it is also liberating. For most of human history, we thought we were the center of everything. We thought the Earth was the center of the universe with everything revolving around us. Then we learned that Earth orbits the Sun. Then we learned the Sun is just one star among many. Then we learned those stars form a galaxy. Then we learned our galaxy is one among many. Then we learned those galaxies form superclusters. Then we learned those superclusters are just small parts of a much larger cosmic web. At each step, we have been knocked down a peg. We are not central, we are not special, we are not even particularly large. We are just here in a small galaxy, in a small corner of an enormous universe. But that does not make us worthless. If anything, it makes us more valuable. Because in all this vastness, as far as we know, Earth is the only place where life exists. We might not be alone in the universe, but we are certainly rare and conscious, intelligent life capable of understanding all this. That might be rarer still. You are made of atoms that were forged in stars that died billions of years ago. Those atoms drifted through space, eventually coming together to form the Earth. And then you are a way for the universe to know itself. Out of all the countless planets in all the galaxies across all of space, you are here able to think about these questions. The Milky Way might be small compared to the universe, but it is your home. Every star you can see belongs to it. Every constellation, every myth and story humans have told about the night sky for thousands of years. All of it comes from our little spiral. Let us talk about the future. Because even though the Milky Way is small, it has a long story still to tell. In about 4.5 billion years, the Milky Way will collide with Andromeda. I say collide, but it is really more of a merger. The two galaxies will pass through each other over the course of several billion years. Despite there being hundreds of billions of stars in each galaxy, actual collisions between stars will be rare. Stars are so far apart that most will pass by each other without incident. But the gravitational interactions will completely disrupt both galaxies' spiral structures. Computer simulations show what will happen. The two galaxies will approach each other, pass through each other, and then fall back together. They will do this dance several times, each pass stripping away stars and gas, until finally they settle into a single large elliptical galaxy. Some astronomers have nicknamed this future galaxy Milkomeda or Milkdromeda. By the time this merger is complete, in about 6 billion years, the result will be a galaxy much larger than the current Milky Way. Milkomeda will contain all the stars from both galaxies, roughly 1.5 trillion in total. It will be a giant elliptical, one of those large red galaxies that have stopped forming new stars. But even Milkomeda will not be that special. It will be one giant elliptical among many others in the universe. Larger than the current Milky Way, sure, but still small compared to galaxies like IC 1101 or A2261 BCG. The merger will also bring us closer to some of the other galaxies in the local group. The whole group will eventually collapse into a single structure over tens of billions of years. This is the fate of galaxy clusters. The largest galaxies consume the smaller ones, growing larger while the small galaxies disappear. But there is another future to consider. The universe is expanding, and that expansion is accelerating. Distant galaxies are moving away from us faster and faster. Eventually, billions of years from now, they will be moving away so fast that their light will never reach us. The observable universe will shrink. Far in the future, any intelligent beings living in Milkomeda will look out at the sky and see nothing beyond their own galaxy. All other galaxies will have been carried away by the expansion of space beyond the observable horizon. They will be completely isolated, unable to see that the universe is larger than their galaxy. In a way, those future astronomers will be back where humanity was a few centuries ago, thinking their galaxy is all there is. Except they will be right, in a sense. For them, the observable universe will consist of just one galaxy. Everything else will be forever beyond their reach. Let us talk about how astronomers figured all this out, because measuring distances in space is incredibly difficult. You cannot just stretch a ruler from here to another galaxy. Instead, astronomers use a series of techniques called the cosmic distance ladder. For nearby stars within a few thousand light-years, astronomers use parallax. As Earth orbits the Sun, nearby stars appear to shift slightly against the background of more distant stars. By measuring this shift, you can calculate the distance. It is the same principle you use when you hold your finger up and look at it with one eye, then the other. Your finger appears to move against the background. For more distant objects, astronomers use standard candles. These are objects whose intrinsic brightness is known. Cepheid variable stars, for example, pulsate with a period that is related to their luminosity. By measuring how bright a Cepheid appears, and knowing how bright it actually is, you can calculate its distance. For even greater distances, astronomers use Type Ia supernovae. These exploded stars all have roughly the same peak brightness, making them excellent distance markers. They are so bright that they can be seen billions of light-years away. The Hubble Space Telescope revolutionized distance measurements by observing Cepheid variables in distant galaxies. Hubble allowed astronomers to measure the distances to galaxies tens of millions of light-years away. The James Webb Space Telescope, launched in 2021, is pushing these measurements even further, observing some of the most distant galaxies ever seen. But here is the thing. All these measurements have uncertainties. The distance to Andromeda, for example, is known to be about 2.5 million light-years, but that number has an uncertainty of about plus or minus 100,000 light-years. For more distant objects, the uncertainties get larger. When we say the observable universe is 93 billion light-years across, that is based on models of how the universe has expanded since the Big Bang. We cannot directly measure distances that large. We infer them from other observations. The point is, astronomy is hard. Measuring the vastness of space requires careful work, sophisticated instruments, and mathematical models. And even then, there is uncertainty. But despite these challenges, astronomers have built up a consistent picture of the universe's scale. And that picture shows clearly that the Milky Way is just a tiny part of something much, much larger. We cannot talk about the universe's scale without mentioning dark matter and dark energy, because these invisible components make up most of the universe. Normal matter, the stuff that makes up stars, planets, and us, accounts for only about 5% of the universe's total energy content. Dark matter makes up about 27%. We cannot see it directly, but we can detect its gravitational effects. Galaxies rotate in ways that only make sense if they contain much more mass than we can see. Galaxy clusters are held together by gravity that is stronger than what the visible matter alone could produce. Dark matter provides the extra gravity. The Milky Way has a dark matter halo that extends far beyond its visible stars. This halo contains about 10 times as much mass as all the visible matter in the galaxy. Without dark matter, the Milky Way could not exist. The stars would fly apart. The galaxy would not hold together. When we compare galaxy sizes, we are really comparing their dark matter halos as much as their visible components. A galaxy like IC 1101 is not just 60 times larger in stars, it is also surrounded by a dark matter halo that is proportionately larger, containing proportionally more mass. Dark energy is even stranger. It makes up about 68% of the universe's energy content, and we have almost no idea what it is. We know it exists because the universe's expansion is accelerating. Something is pushing space apart. And that something is what we call dark energy. Dark energy is causing distant galaxies to move away from us faster and faster. Eventually, it will tear apart even gravitationally bound structures like galaxy clusters. Billions of years from now, dark energy might even overcome the gravity holding galaxies together, ripping them apart star by star. This means that even though the Milky Way seems small compared to the universe now, it might be relatively larger in the future. As dark energy pushes structures apart, making the universe less dense, galaxies like the Milky Way will become more isolated. In the far future, the Milky Way and its merged form with Andromeda might be one of the few remaining structures in a vast empty universe, but that is billions of years away. For now, the universe is still full of galaxies, superclusters, and cosmic structure. And the Milky Way remains a small part of that structure. So, what does all this mean for us practically? Does it matter that the Milky Way is small compared to the universe? Does it change anything about our daily lives? In one sense, no. You still have to go to work, pay bills, deal with the same everyday problems as always. The fact that the universe is vast does not change any of that. But in another sense, yes, understanding our place in the universe changes how we see ourselves and our world. Every boundary we have ever fought over, every disagreement we have ever had, plays out on a planet orbiting one star among hundreds of billions in a galaxy that is one of trillions. The astronomer Carl Sagan talked about this when discussing the pale blue dot photograph. That picture shows Earth as a tiny speck in a sunbeam taken from the edge of the solar system by Voyager 1. Sagan said that everyone we love, everyone we know, every human who ever existed, lived out their lives on that speck. All our triumphs and tragedies, all our wars and peace, all of it happened on that one small world. And that world orbits a star in a galaxy that is small. Not the smallest, but definitely small compared to what is out there. This perspective doesn't make our lives meaningless. If anything, it makes them more meaningful because we are here able to understand all this. We are the universe becoming aware of itself. The Milky Way might be small, but it is your home. And as far as we know, Earth might be the only place in this vast universe where life has arisen and become conscious. That makes us precious, not worthless. Astronomers are still discovering new things about the universe's scale. New telescopes are being built. New observations are being made. Our picture of the cosmos continues to evolve. The James Webb Space Telescope is already sending back images of galaxies that existed when the universe was very young, less than 1 billion years after the Big Bang. These early galaxies are smaller than the Milky Way, often by a lot. They are the building blocks that merged over billions of years to form the large galaxies we see today. Studying these distant galaxies helps us understand how the Milky Way formed. Our galaxy did not spring into existence fully formed. It grew over time, consuming smaller galaxies and gathering mass. The Milky Way we see today is the result of 13 billion years of evolution. Future telescopes will see even further. Plans are being developed for instruments that can observe the very first stars that formed in the universe. These observations will help us understand how structure formed, how galaxies grew, and how the universe evolved from a nearly uniform soup of hydrogen and helium into the rich tapestry of galaxies we see today. But no matter how powerful our telescopes become, we will always be limited by the observable universe's boundary. We can never see beyond that horizon. The universe beyond our view will remain unknown, possibly forever. Still, the search continues because even though the Milky Way is small, even though we are just one tiny part of an enormous universe, we want to understand it. That drive to explore, to question, to seek knowledge is one of the things that makes us human. But now, let us zoom back in. Let us come home. Because no matter how small the Milky Way is compared to the universe, it is still our galaxy. It is still home. When you look up at the night sky on a clear, dark night, away from city lights, you can see the Milky Way stretching overhead like a river of light. That band of light is the combined glow of billions of stars too distant to see individually, all part of our galaxy's structure. Every star you can see with your naked eye is part of the Milky Way. Sirius, the brightest star in the night sky, is about 8.6 light-years away. Betelgeuse, the red giant in Orion, is about 700 light-years away. Alpha Centauri, the nearest star system to our Sun, is about 4.3 light-years away. All of them are our neighbors in this vast spiral. The Milky Way has been humanity's companion for as long as we have existed. Ancient cultures created myths about it. The Greeks thought it was milk spilled by Hera. The Norse thought it was the path to Valhalla. Native American tribes saw it as a path of souls traveling to the afterlife. Chinese astronomers called it the Silver River. We did not know what it really was until relatively recently. But even in our ignorance, we recognized its beauty. We told stories about it. We wondered about it. Now we know what it is. We know it is a galaxy, one of trillions. We know where it fits in the largest structure of the universe. We know how small it is compared to what is out there. But that knowledge does not make it less beautiful. If anything, it makes it more beautiful because now we understand what we are looking at. We know that each point of light in that band represents another sun, perhaps with planets, perhaps with life. The Milky Way is small, but it is ours. And within it, on one small planet orbiting one ordinary star, life arose. Consciousness emerged. And now, 13.8 billion years after the Big Bang, the universe has produced beings capable of understanding their place in it. The question we started with was the true scale of our Milky Way in this vast universe. And the answer is breathtaking. Zoom in, and we live in one of the cosmic giants. A galaxy so large that 95% of everything else out there is smaller. Zoom out, and even our mighty spiral becomes just one flickering light in an ocean of 2 trillion others. That duality is everything. The Milky Way gave us hundreds of billions of stars, a quiet corner stable enough for life to appear, and 4 billion years of calm evolution that let consciousness emerge on one little world. Every human story, every love, every dream, every discovery, all of it, unfolded here inside this one extraordinary galaxy. The universe is unimaginably large. Countless superclusters, walls, and voids stretch farther than light has had time to travel. Yet you are here right now, awake inside one of the biggest islands in that endless sea, feeling the full weight and wonder of it all. So when you look up tonight at that glowing band across the sky, remember it is vast enough to be exceptional and still just our home. And that makes it perfect. There is something profound that happens when you truly grasp the scale of the universe. It changes you. Not in some vague, mystical way, but in a real practical sense. Your perspective shifts. The problems that seemed overwhelming yesterday suddenly seem smaller, not because they are not real or important, but because you see them in context. That argument with a friend, that stressful day at work, that disappointment you have been carrying, all of it is happening on one planet, in one solar system, in one galaxy, among trillions. This is not about minimizing your problems. Pain is pain, and suffering is suffering regardless of cosmic scale. But there is something freeing about understanding that the universe does not revolve around your personal drama. The cosmos will continue its slow, majestic dance, whether you succeed or fail at whatever you are trying to do. At the same time, this perspective makes the moments of joy, love, and connection more precious because they are rare. As far as we know, Earth is the only place where life exists. And conscious life capable of love and art and music and wonder, that might be even rarer. Every human interaction, every moment of beauty, every act of kindness is an extraordinary thing. Not because some divine plan says so, but because it is genuinely unusual in a universe that is mostly empty space and unconscious matter. The Milky Way might be small, but it produced you. And you can love, think, create, and wonder. That is remarkable. What does the future hold for our understanding of the universe's scale? We are limited by technology right now. Our telescopes can only see so far. Our theories can only predict so much. But technology improves. The next generation of telescopes will see deeper into space and further back in time. We will observe galaxies that formed even earlier than the ones we can see now. We will get better measurements of distances, galaxy sizes, and the universe's expansion rate. There are plans for telescopes in space that will dwarf even the James Webb Space Telescope. Ground-based observatories with mirrors 30 meters across are being built. These instruments will revolutionize our view of the cosmos. We might discover that the universe is even larger than we thought. We might find evidence for or against the multiverse hypothesis. We might detect signals from other civilizations or find biosignatures in the atmospheres of distant planets. Or we might discover something completely unexpected, something that changes everything we think we know. That has happened before. Every major advance in astronomy has revealed surprises. There is no reason to think we have seen the last surprise. But even as our knowledge grows, some things will remain constant. The Milky Way will still be our home. The universe will still be vast, and we will still be here looking up, wondering, trying to understand our place in it all. There is a paradox here that is worth holding in your mind. Compared to the greatest structures, the walls, the voids, the observable universe itself, even our mighty Milky Way becomes just one flickering light among trillions. Yet that same galaxy is one of the true giants of the cosmos. Larger than 95% of everything else that exists. That duality is everything. A seed is tiny, almost nothing, yet from it grows a tree that can outlive mountains. An atom is unimaginably small, yet atoms build stars, worlds, and you. The Milky Way sits in the same perfect balance, vast enough to cradle hundreds of billions of suns, stable enough for life to arise, rich enough in heavy elements for planets and consciousness to emerge. Within this one extraordinary galaxy, at least one world learned to look back at the sky and understand what it was seeing. The universe may be incomprehensibly large, but most of it is silent and empty. Our Milky Way, exceptional in its size, remarkable in its story, is different. It has us. One of the most sobering realizations that comes from understanding the universe's scale is how isolated we are. The distances between stars are vast. The distances between galaxies are even vaster. Even if the universe is filled with life with civilizations, we might never meet them. The nearest star system, Alpha Centauri, is about 4.3 light-years away. With current technology, it would take thousands of years to reach it. Even with hypothetical future technology traveling at a significant fraction of light speed, it would take years or decades. The nearest large galaxy, Andromeda, is 2.5 million light-years away. Even traveling at the speed of light, which is impossible for anything with mass, it would take 2.5 million years to reach it. For practical purposes, it is unreachable. Most galaxies are billions of light-years away. We can see them, we can study them, but we can never go there. We will never know what they contain. They will remain forever beyond our reach. This isolation is profound. We are confined to our little corner of space. The Milky Way is our home, and it is likely the only home humanity will ever have. We might spread to other stars within the galaxy over thousands or millions of years, but we will never leave the galaxy itself. In a way, the Milky Way being small is a blessing. A larger galaxy would be even more impossible to explore. At least with the Milky Way, there is a chance that humanity's descendants, given enough time, could explore a significant fraction of it. but that is far in the future. For now, we are confined to one planet orbiting one star in one small part of one medium-sized galaxy. Understanding the true scale of our Milky Way, one of the cosmic giants, yet just one island among trillions, should make us cherish this rare paradise even more. We speak of climate shifts, vanishing species, the fragile balance of our world. Sometimes these challenges feel distant, almost abstract. But pause and remember, as far as our telescopes can see, Earth may be the only place where oceans reflect sunlight, where forests breathe, where minds like yours have awakened beneath an open sky. In a universe of silent voids and burning stars, this pale blue dot is the only home we have ever known, possibly the only one conscious life will ever have. We won the greatest lottery of all simply by being born here in a stable corner of one of the universe's grandest galaxies. Liquid water, breathable air, a magnetic shield against the solar wind, a climate gentle enough for billions of years of evolution. These are not ordinary. They are miracles wrapped in everyday light. And now, for the first time in cosmic history, the actions of one species on one small world can decide whether this miracle continues. That is not a burden. It is a privilege. A quiet, immense responsibility carried by stardust that learned to care. Our Milky Way is vast and magnificent, home to hundreds of billions of suns. Yet Earth is infinitely precious within it. It is the only place we have. Perhaps the only place anyone ever will have. That alone is reason enough to protect it. Not out of fear, but out of wonder, gratitude, and love. Despite everything we have learned, despite all the measurements and comparisons and vast numbers, the universe remains wondrous. The fact that we can understand it at all is remarkable. Think about what science has achieved in just a few centuries. We have gone from thinking Earth is the center of everything to understanding our place in a vast cosmos. We have measured the distances to galaxies billions of light years away. We figured out how stars work, how galaxies form, how the universe began. All of this was accomplished by curious humans looking up at the sky and asking questions. No divine revelation told us the answers. We had to figure it out ourselves through observation, experimentation, and reason. And we are not done. Every answer raises new questions. Why is the universe expanding? What is dark matter? What is dark energy? Are we alone? What lies beyond the observable universe? Is there a multiverse? These questions will occupy scientists for generations to come. Maybe we will find answers. Maybe we will find that some questions are unanswerable. But the search itself is valuable. The Milky Way might be small, but it produced beings capable of asking these questions and seeking answers. That is something to be proud of. We have covered a lot of ground tonight. We started with the Milky Way and zoomed out, comparing it to ever larger structures until we reached the observable universe itself. And along the way, we discovered something fascinating, something paradoxical. The Milky Way is simultaneously one of the largest galaxies in the universe and also incredibly small compared to the largest cosmic structures. Both of these things are true at the same time. When we compare the Milky Way to most galaxies, to the dwarf galaxies that make up 95% of all galaxies in the cosmos, the Milky Way is enormous. It is a giant, a massive spiral containing hundreds of billions of stars. Most galaxies will never be this large. Most galaxies are tiny collections of a few billion stars or less, faint and unremarkable. The Milky Way is exceptional. It is in the top 5% of galaxies by size. That is genuinely impressive. If galaxies were countries, the Milky Way would be one of the superpowers, not a small island nation. But when we compare the Milky Way to the largest galaxies, to the supergiant ellipticals, like IC 1101 or M87, then yes, it is smaller. These galactic monsters contain trillions of stars and span millions of light years. They dwarf the Milky Way. And when we zoom out even further, when we look at superclusters and cosmic filaments and the observable universe itself, the Milky Way becomes just one galaxy among trillions. A large galaxy, yes, but still just one piece in a structure so vast it defies comprehension. This is the true scale of the Milky Way. It is not small, it is not average, it is large, genuinely large by any reasonable standard. But the universe is so vast that even a large galaxy becomes insignificant when you zoom out far enough. It is like being a tall person in a large crowd. You might be taller than 95% of the people around you. That makes you tall. But stand next to a skyscraper and suddenly your height seems irrelevant. Both things can be true. You can be tall and also tiny, depending on what you are comparing yourself to. The Milky Way is our home. It is the galaxy that produced the Sun, the Earth, and us. It is the structure that contains every star visible to the naked eye, every constellation that ancient humans used to navigate and tell stories, every astronomical object that humans have observed throughout history. And it is large, genuinely, impressively large, larger than almost all other galaxies. That should give us some perspective, some appreciation for the cosmic neighborhood we inhabit. But I want to end on a different note because, while the Milky Way might be small, it is also home. And there is no place quite like home. When you go outside tonight and look up at the sky, try to see the Milky Way. It is harder if you are in a city because light pollution washes it out. But if you can get somewhere dark, away from streetlights and buildings, you will see it. A pale band of light stretching across the darkness. That is your galaxy. That is where you live. All those points of light, all those stars, they are your neighbors in space. Some are closer, some are farther, but all of them are part of the same structure that holds you. The universe is vast. The Milky Way is small, but you are here on a planet in this galaxy, able to think about these things. And that is worth something. That is worth a lot, actually. So yes, the Milky Way is small compared to the universe, but it is also everything we have. It is home. And sometimes home is enough. Let me leave you with one last thought. The question of scale, of how large or small the Milky Way is, ultimately reveals something profound about perspective. Because scale is relative. It depends entirely on what you are comparing. To a human, the Milky Way is unimaginably large. You could live 1 billion lifetimes and never visit even a tiny fraction of its stars. To a dwarf galaxy, if it could somehow perceive such things, the Milky Way would be a giant, a massive structure hundreds of times larger than itself. To the universe, the Milky Way is one galaxy among trillions, large compared to most, small compared to some, and insignificant compared to the largest cosmic structures. All of these perspectives are valid. All of them are true. The Milky Way is simultaneously enormous and tiny, important and insignificant, exceptional and ordinary. It depends on your frame of reference. What matters is that we understand this. We understand that our home galaxy is genuinely large by most standards. We are not living in some tiny, insignificant corner of the universe. We are living in one of the largest galaxies that exists. That is something to appreciate. But we also understand that no matter how large the Milky Way is, there are always larger structures. There is always a bigger picture. The cosmos operates on scales that dwarf even the largest galaxies. The Milky Way gave birth to us. It is genuinely large by cosmic standards, sitting in the top 5% of all galaxies. But it is also part of structures so vast they make even a large galaxy seem small. Both things are true. So when someone asks about the true scale of the Milky Way, you can answer with confidence. You can explain that it is one of the largest galaxies in the universe, home to hundreds of billions of stars. You can talk about how most galaxies are tiny dwarfs, by comparison. But you can also explain that when you zoom out far enough, when you look at superclusters and cosmic filaments and the observable universe itself, even a large galaxy like ours becomes just one small piece in an incomprehensibly vast cosmos. The Milky Way is large, but the universe is larger. And understanding both of these truths, holding them in your mind at the same time, that is what it means to truly grasp the scale of our cosmic home. Thank you for joining me on this journey. If you found value in this exploration, please consider liking this video and subscribing. Your support helps me continue making these deep dives into the cosmos. And remember, the next time you look up at the night sky and see that band of light stretching overhead, you are looking at home, one of the largest galaxies in the universe. Genuinely, impressively large, home to hundreds of billions of stars. And yet, when you zoom out far enough, just one galaxy among trillions in a cosmos so vast it challenges comprehension. The Milky Way is large. The universe is larger, and you, living in this remarkable galaxy, are part of it all. Sleep well under the stars. The Milky Way is vast, and you have your place in it, right here, right now in this large, precious galaxy we call home. Good night, and sleep well under the stars. Despite everything I have told you tonight, despite all the measurements and observations and theories, there is still so much we do not know about the universe and how the Milky Way fits into it. Let me highlight some of the big open questions. We still do not know what dark matter is. We know it is there because we can measure its gravitational effects. But we do not know what particles it is made of, or if it is particles at all. It could be some exotic form of matter we have never encountered. It could be black holes. It could be something else entirely. This is one of the biggest mysteries in physics. We also do not know what dark energy is. We know it is causing the universe's expansion to accelerate, but we do not know why. Is it a property of space itself? Is it a new kind of field? Is it something to do with how gravity works on cosmic scales? We do not know. We do not know if the universe is finite or infinite. The observable universe is finite, obviously, because we can only see a certain distance. But the actual universe beyond what we can see could extend forever. Or it could curve back on itself being finite, but without an edge like the surface of a sphere. We have no way to know. We do not know if there are other universes. The multiverse idea is popular in some physics theories, but there is no observational evidence for it. We might never be able to test it. It might not even be a scientific question if it cannot be tested. We do not know if we are alone in the universe. The Fermi paradox remains unsolved. Are we the only intelligent life in the galaxy, in the universe? Or are there countless other civilizations out there that we have not detected yet? This is maybe the most profound question we face. We do not fully understand how galaxies form and evolve. We have good models, but there are still surprises. The James Webb Space Telescope is finding massive galaxies in the early universe that should not exist according to our models. Either those galaxies formed faster than we thought possible, or our models are wrong. We are still figuring it out. We do not know what will happen to the universe in the far future. Will the expansion continue forever, leading to a cold, dark, empty universe in the distant future? Will something else happen? Could dark energy somehow change, reversing the expansion? We have theories, but we cannot be certain. All these unknowns remind us that science is a process, not a destination. Every answer leads to new questions. Every discovery reveals new mysteries. The story of the Milky Way and its place in the universe is still being written, and it probably always will be. But here is what is remarkable. The fact that the Milky Way is large does not diminish the vastness of the universe. And the vastness of the universe does not diminish the impressiveness of the Milky Way. Both can be true simultaneously. The Milky Way is large, but it contains hundreds of billions of stars, countless worlds, and at least one planet where life arose and became conscious. It contains the entire human story, all our art and music and science and love. It contains you. Being one of the largest galaxies in the universe means something. It means we are not in some insignificant corner of the cosmos. We are in a massive, impressive structure that towers over most other galaxies. And yet, we are also part of something even larger. Structures that span hundreds of millions or billions of light years. This is the true scale of the Milky Way. Large enough to be exceptional, small enough to be part of something greater, perfect in its paradox. So yes, the Milky Way is large, genuinely, impressively large, but the universe is vast beyond comprehension. And that makes our cosmic home both exceptional and humbling at the same time. Thank you for spending this time with me tonight, exploring the scale of the cosmos and our place in it. I hope you found it interesting, maybe even enlightening. If you did, please like this video and subscribe to the channel. It helps more than you know. And the next time you look up at the night sky, remember what you have learned. That band of light is the Milky Way, one of the largest galaxies in existence, home to hundreds of billions of stars, exceptional by any measure, and yet part of structures so vast they make even a large galaxy seem small in comparison. The Milky Way is large, but the universe is larger. And both truths make our cosmic home all the more remarkable. Good night, and sleep well under the stars.